All right, it's recording now.
Okay, so what I did last year when I was doing my final for this class, I made a review sheet for exam one. It's kind of a little long. If you guys care about that?
Nope. The more the
All
better.
right, all right, got it. Okay, so let me first get to it. Okay, so basically what I did was I made notes for each section, and then I just gonna practice some problems for you guys. So let's start off with wave function. Everybody knows what wave function is. It contains all the info, and we use operators to extract the information from that wave function. And a wave function can specify space, but like x, y, and z for q and time. So you guys are going to deal with only time independent wave functions. And when you square the wave function on a second bullet, you see that you get the probability density. And the wave function must satisfy the condition where if you integrate over all space, the probability density, it has to equal 1, which means it's 100% probability of finding that particle. And that makes sense. That's basically saying when you integrate, if I look all the way to the left infinitely and it's all the way to the right, I'll always find that particle, no matter what.
Are you sharing
And
something?
if the, oh, I forgot to share a screen, sorry. Yeah, screen. Yeah, I thought I already shared it. Okay.
No, you're good.
All right, like I was saying before, it's 100% probability of finding the particle if you look all the way to the left and all the way to the right, basically all space. Does that make sense, everyone?
Yeah. Yeah.
All right, and so when you normalize, all you're really doing is making sure that when you equaling it to 1 for all space, you're making sure that n just normalizes it. Make sure that the integral when you square the probability is equal to 1. So the equation to find the normalization constant is basically this here. So basically you solve the integral and then whatever that wave function is. And then after that, you put it over 1 and then you put it to half power. And then you plug in the normalization constant into the original equation. You multiply to the original equation, which is this. And that'll be your wave function. That'll be your normalized wave function. All right. And everybody knows what complex conjugates are, right?
Yeah.
You basically, okay, so you basically apply the complex conjugate that turns I into negative I. And the reason why I use complex conjugate when multiplying so that the i's cancel out. And so when you're finding the probability density that something has i's in it, you multiply by its complex conjugate. So that way its probability density is always positive. And the wave function must satisfy these conditions. They must not have multiple values at a variable. So at like the x-axis, it must not have like at like x equals 1. It can't have multiple values at x equals 1. And it must be continuous, and its first derivative must be continuous. And the probability must, if you were to integrate like overall space, probability must not exceed infinity. It must be like a finite value like 1 when you integrate. And this is just a question. So let's say if you're trying to test if these values here are good wave functions, like these functions. So what you would do is get a graphing calculator, and I'll show you what the first one looks like. So it's from 0 to, let's say, infinity. And I think the tan is going to look mostly like this. And sorry for the bad drawing, but basically, yeah, if you were trying to see if this is a good wave function or not, based on our other definition, we would see that this wave function is not continuous. It's not connected at all, which means this would be a bad wave function. So the first one is a bad wave function. And then we move on to the second one. So the second one would be x to the 1/2. So it starts at 0 to infinity, x to the 1/2 and e to the negative a/2. And then so it starts at 0 and then it goes up and then decays all the way down. And so this decays as x goes to infinity, and and it's like at zero. So this would make a good wave function because it's continuous. And oh, I forgot. Let me just put this here. It has to approach zero as x goes to negative positive infinity. I forgot to note that here. So it goes to zero at zero, and it decays at infinity as it goes to infinity. So this would make a good wave function. So you could check this here. And then the next one will be assigned. So it'll go up, down, and up, down. And it goes up and down infinitely. But when you try to find the probability of this will be infinity because it doesn't decay at all. And it just goes straight up, straight down, straight up, straight down. Does that make sense to everyone?
Doesn't
Okay. You have a
what's it
question?
called?
Yeah.
Yeah, no, it's good.
You good? Okay. Anybody else have a question, or you're all good? Okay. So from this question, the second equation would be a good wave function to use. And the reason for it is it satisfies all the conditions. So it's the limit as that wave function goes to a positive or negative, I'll just say infinity, is equal to 0. And at 0, it's equal to 0. And it's continuous. And its first derivative is continuous. And you can tell if its first derivative is continuous if it doesn't make any sharp turns like this. If it does, that means its first derivative is not continuous. And if you can't truly tell, you can take a derivative of that function and graph it on the bounds to see if it's continuous. And yeah, that's pretty much it. Let's see. All right. An operator is linear if it applies linearly to the function. So if you apply operators separately to each term and add them together, and it's equal to if you were to apply the operator to the whole term here, then that means it's linear. So stuff like derivative operator is linear, and yeah, the x operator is linear, and stuff like that. So basically, any constant times that, or any derivative would be linear. So, and I didn't orthogonality, I think you guys went over it a bit. I don't think you need to learn it for this exam. It just basically means if I were to multiply two functions together, and if I were to integrate over all space, then and if they were equal to 0, that means they're orthogonal. And let's go to the next part. And I just list over the basic operators to know, like the momentum, X operator, Hamiltonian, and all that stuff. And a Hamiltonian, it can be different for different systems. So like particle in a box, this would equal to 0, or particle in free motion that's going straight forever. It has no potential unless it goes under a barrier. And yeah, and that's pretty much it with Hamiltonian operator. And the momentum operator squared is just basically the momentum operator applied again, so 2 times. So the second derivative, and I'll just remove the f here. The second derivative and multiply by h bar. Okay. Pretty much. And the most important part is eigenvalues and eigenfunctions. So if you were to apply the operator and the function is unaffected by that operator, which means that it's not multiplied by x or anything, then that means it's the an eigenfunction of that operator, and whatever constant is multiplied by the effect of that operator is the eigenvalue, which is a measurement that's taken based by applying the operator. Okay. What's the next one? So consider a particle in free motion, and is the function this function here an eigenfunction of the momentum operator? If so, what is its eigenvalue? So first off, you start with applying the operator. So you get And that's just negative IH bar, derivative onto E X. And then when you apply the operator, you get negative IH bar, and then you get IK1 and E to the IK1 X. And what you're going to get is I times I is -1 times -1 is just 1. So it's going to be H bar K1 times E to the negative. Now from here, you see that the function is maintained. It's not multiplied by any X or any X word or anything like that. And it's just the result is just a constant. So this is just a constant here. And so this means that this is the eigenfunction of the momentum operator. And this is its eigenvalue. Does that make sense, guys?
Yeah.
Okay, so if you guys have any questions, just let me know so I can clear it up. Okay, and
I have
the
a
part
quick
B.
question.
Oh, what's up?
So if there's a variable, say like X, mixed in with the H bar K and I, would it still be an eigenvalue?
It would not, because it's basically saying that X is the eigenvalue is dependent on X, which would not be true for an eigenvalue. An eigenvalue has to be a constant. And to be an eigenfunction, it can't be multiplied by a variable or anything. So yeah.
Okay, thank you.
All right. Let's go with part B. And it's asking to do the same thing with this function to see if it's an eigenvalue. So what you do is apply this. And that's going to be, so that momentum operator is a linear operator, which means you can apply it linearly to the function. And this is going to equal to operator. Okay. We saw this before. We found it to be HK. 1. That's going to be the opposite. So it's going to be negative H bar K2. And that'll be E to the I K2 X. And if you try to pull this out, you would get B here. And then A. Okay.
Why do you have
so looking.
Oh, sorry. I
Oh,
was just
say that
gonna
again.
ask, why do you have a negative H next to your B?
Oh, because when I take the derivative of this, it's gonna be I times I. Oh wait, I think I understand. Yeah, it's supposed to be positive here.
Okay.
Yeah, I was thinking it's a negative I. Okay. So, okay, that's your answer. And from looking at this, guys, would you think that this is an eigenfunction of the Hermitian operator?
No.
Yeah, it's not. And it's because you can't pull out both of these values here. See, K1 and K2 are different, and you can't pull it out of the function. And that means it can't be an eigenfunction of the momentum operator. Does that make sense?
Yeah.
Yeah, because it has to be a constant multiplied by the whole function, and this here is the whole function, this here. If they were both equal, if K2 was a set K1, then you could call it a constant and it would be an eigenvalue. All right. All right. And you guys know about hermiticity? Yeah. I'll just explain
No.
it.
Can
So
you?
if
Yeah. Can you go
yeah,
through it?
so yeah, definitely. I'll go with the second derivative, but this walks you through how to prove something's Hermitian. So to prove it, d of dnx is Hermitian, like the derivative operator, what you have to do is basically use the integration by parts to put the derivative on the other side of the function. So you have to put the derivative here on f of x after using integration by parts. So from using integration by parts, you put the so you're trying to put the f here on, make this have a derivative on it, and I want to take derivative off of g. And what we're trying to do, if you look around here, is make sure this is right if I were to put a derivative onto f. I should have wrote the term down, but I'll go more in depth on my example. But basically, you see if you apply a derivative here, and this is not negative, if you apply the derivative on the other side. So basically, you do integration by parts, and then you see that I believe the overall result you get is this, and this will be that f is not this would be not Hermitian. So derivative operator is not Hermitian. And if you're confused about this, I'm going to go more in depth on my example, and just to let you guys know, x is Hermitian, because x you could just multiply x by g and doesn't really matter. X by g or f by g, and doesn't really matter how you where you put x at. Okay. So determine whether the following operator is Hermitian. So first step is you find, so f, then 2g. Actually, I'll just do this. Okay. And this is equal to, we were trying to prove this is right. Okay. So we're trying to put the derivative onto f. So what I like to do here is, if I'm trying to put the derivative onto f, I put u as f, and I put du as dv. I mean, put dv as g, because we're trying to take off a derivative. So we start off with f, and trying to take off a derivative on g. So I mean, in this case, it would be g double prime. G double prime is just the second derivative of g. And so we take the derivative of this and we get f prime. And integration by parts, you do the opposite to the integral of this would be g prime. And then from here, you would, so it's the equation for integration by parts is this, e du, and this is going to be equal to, yeah, so you do f times g prime from negative infinity to infinity. This will be minus v, so it'd be g prime times f prime. Since these are just arbitrary functions, when you integrate negative infinity to infinity, this will equal to 0. And then you would just have to do integration by parts again. Now, if this was, let's say if this was the first derivative, you would stop at this step. And then because in this case, it'll be f to f prime, it'll be g prime to g. Does that make sense, guys?
I kind of lost you there.
So if this, in case, let's say if I was doing the first derivative instead, then it will be g prime instead of g double prime, right? And when you take the derivative of, the integral of this will just be g. So when you do your integration by parts, you'll have like g prime, you'll have g times f prime, and that will be not Hermitian. Like you're basically, what I'm basically saying is you're just gonna do this once if it was the first derivative, because all I'm doing is taking the derivative off of g once and putting it onto f once. Since we have a second derivative, we're taking off the derivative off of g 2 times and putting it onto f. Does that make sense?
Yeah, I got it that time. Thank you.
Okay. So from here, we do the integration by parts again. So then we have u is equal to f prime, and du is equal to f double prime, and then dv is g prime, and v is equal to g. And we saw from our equation that is uv, so it's going to be f prime times g from negative infinity to infinity. And it'll be minus the integral from g times f double prime. And this will be parentheses negative, because we have a negative sign here. And then these are just arbitrary functions. This will be 0. And then you're just left with negative times negative is positive. So it's just negative infinity. And since we have f double prime derivative, we have inside we have df g. And this means that the second derivative is Hermitian, since we proved that up here. You 100% with this, guys? That makes sense?
Sort of, not really. But we can keep going.
So what does the dx over dx squared do?
Dx over dx squared this year.
Yeah. Like how did you plug it in? Yeah.
So that's the second derivative operator. I'm just showing, so this here is on G, and what I'm trying to do is put it on F.
Wait, do you have a laser pointer?
Yeah. A laser pointer? Yes, I do.
Charge your iPad first. You can't let that die.
Oh yeah. Give me 1 second. I forgot.
Take your time.
Sure,
you're good. You're good.
Okay.
So
but the overall.
Oh, yeah.
What were you about to say?
Oh, I was just gonna say we're transferring the double derivative from G to F.
Yes, that's the
Hermitian means?
Hermitian just basically means, it's the first definition here. If you see right here, it's on the first line. I'm trying to prove that if I were to apply the derivative onto G, it'll be the same as if I were to apply it onto F.
Oh, okay.
So if it was an operator, it'll be like, if I apply an operator onto G, it'll be the same as applying it onto F. And so, yeah. It's terrible. That's a terrible angle. Please plug in. Okay, thank you. Okay. Whew. All right. Next part. All right, particle in a 1D box. So particle in a 1D box, I think the only thing I want you guys to take away from this is the bounding conditions. So the particles in the box, meaning that from its bounding conditions, the potentials outside are infinity, which means that the particle can't exit outside the box. And because of that, you can't, it's only confined to that box. And so it's, when it comes to all space, when you're integrating, the particle can only exist in the box, so that so all space would be between 0 and L, which is the length of the box. Does that make sense?
Yep.
Okay. So from here, the box is length L. Okay, what I basically just said, and the region 1 and region 2 are basically the same, and they're equal to 0. And here's the energy equation. Oh, let me put the energy equation here. From applying the Hamiltonian operator, the Hamiltonian operator would just be this term here, since the potential inside the box is equal to 0. And so after applying the Hamiltonian, you can get this eigenvalue. And we can, instead of applying an operator every single time, we can just use this equation here. And the particle in the box can exist in multiple quantum levels. Okay. All right. Good. And also, when it comes to the next energy level, so the difference between each energy level is described by this equation. So if you were to increase the n level, the spaces between each level would decrease. And this is shown here. So as n goes to infinity, differences between each energy level will decrease towards 0. And a node is basically when the probability, when the wave function is equal to 0, and when the probability density is equal to 0. And the antinode is basically when the max or minimum on a wave function. So if it, let's say for n equals 1, it's basically at a maximum, that's the antinode. And if it was at a minimum, it will be an antinode. And that's only for a wave function. For a for probability wave function, the minimum will just be flipped because the minimum is always negative, so it'll just be flipped here. And so antinode is always the maximum on a probability wave function, a particle in a box. And a particle box can be described with this equation here. All right, let's see what else. And these are just the expectation values of the particle in the box. All right. And you get, just to review expectation values. Expectation values literally is you're applying the operator onto the wave function and then multiplying that result by the original wave function. So if I were to apply the operator, let's say I take derivative of this, then I multiplied the original wave function, and then I integrate over all space. And then let's see what else we got. Stationary system. All right. And also to make sure, actually, I think that's pretty much it. All right. So problem 1 is asking you to determine the expectation value of the momentum operator squared. So I kind of set it up for it a bit. So like I said before, you apply the operator first onto, so this is the momentum operator squared. So you apply the operator first, and then after applying the operator, you you multiply it by original wave function. So let's apply the operator. H bar squared. And I'll just multiply it inside of it, so I don't have to worry about the product rule. So that's going to be 8xa minus x squared. So this is going to be equal to negative h bar squared. And this is going to be the first derivative. Take the derivative of 1, so I get a minus 2x. Take a derivative again, I get minus 2. And this is just going to be equal to 2h bar squared. So P of X squared, and that's going to be equal to 30 over A. And that's just a normalization constant. So these are both constants in front. So I just have to just square this because on the wave function, times the wave function. And so you get 30 over A. And this is just a constant. So you can put this on the outside. 2h bar squared. And then the integral on the inside. And then I just need to solve, okay, xa minus x squared.
I have a question.
What's up?
Over here, hold up, let me annotate. Oh, I can't annotate. Anyway, where you have the 30 over A and then you have the integral 0 to A, what's that n?
Yeah.
What's the n
Oh,
squared
that's just,
doing there?
oh, that's just to tell you guys that it's just the normalization constant squared. This here is the normalization constant. And when you multiply
Oh,
by the wave function, yeah, when you multiply by wave function, it's going to be n squared. In this case, 30 over A squared, which is just 30 over A.
okay.
That's not really in the equation.
Okay.
Make sense?
Yep.
Okay.
I
So
have a
from
question about like about what you did in the calculation. So all you did was you took the derivative of x times a minus x twice, right? And everything else was just
yeah,
brought down. Is that what happened?
yeah, that's what I did. That's what I did here.
And also, so at the top you have x minus a x, like x times a minus x, and then x times a minus x twice. So what happened to? Oh, did you just? Yeah, what happened to the first one?
The first one is still here. It's down here. I just multiply by x over here. And I'm multiplying by the result of the operator, which is just this. And I put this on the
Okay, I
outside because
see.
it's constant.
Got it. Yeah, that makes sense. Thank you.
No problem. Okay. So from solving the integral, you get 30 over A. And, oh, let me just go back. So 60 h bar squared over A. And then you have the bounds from x squared, I believe. Yeah, x squared over 2 minus x to the third over 3. So we don't have to worry. So when we take the bounds, we just plug in A minus, we just plug in A and then we plug in 0 and we subtract by each other. But since if we plug in 0, this will just be 0. We just have to worry about A. This will be 60 h bar squared over A, and then that'll be a to the third minus 2, I mean over 2 minus a to the third over 3. And this will just equal to 60 h bar squared over A. That's a to the third over 6. And I'll just put my answer over here, which is just 10 h bar squared times a squared. Yeah, that's the answer. Does that make sense, everyone?
Yeah.
Okay.
I have a question,
What's up?
just real quick. I just want to double check. The reason why you have negative h bar squared is because you did I squared, right? Which just turns into -1.
Yes.
Okay, just double checking. Thank you.
Yeah, no problem. Let me just double check momentum operator. Okay, yeah. Yeah, and when I reiterate, it's negative I times negative I, which would be -1. Okay, so let's go to the next part. Okay, So it's asking us to sketch the wave function, which I did already, and so let's say we have this, and we want to and they're saying, okay, this is our trial particle in the box wave function, and it's saying that we want us to sketch that function and below in the axis below, and it's also asking, is the function a reasonable wave function for such a purpose? Now, based on this, would you guys say, okay, I put the answer here, but it makes a good wave function because if you see here, think about this. This is basically a particle in the box, which means this is the infinite potential. And as it goes to negative infinity, the waveform is going to be 0, and over after infinity is going to be equal to 0, like after a and before 0. And so it's going to be 0 at both its boundary conditions, which makes it a good wave function, meaning if you integrate for probability, it won't be infinity. And also it's because it's continuous and it's all connected here. Does that make sense to everyone?
Yeah.
Yeah, okay. And this is the ground state, okay. If the wave function given below is not normalized, find a normalization constant n. You may find the following useful. Okay. So it's basically telling us to integrate for this. And I mentioned before how if you want to find it, so you solve this interval, and after solving for this, you just basically do this to find a normalization constant. And so we have to solve this integral, and then we have to solve for n. Okay, so from here, you can multiply, and you'll get x squared times a minus x. And then from here, you can multiply whatever a minus x is, and this will be a squared minus 2ax minus plus x squared. And you multiply x inside, which would be x squared times a squared minus 2ax to the x to the third plus x to the fourth. And then after integrating, you find this is true. X to the third a squared over 5, over 3 minus 2 a x to the fourth over 4 plus x to the fifth over 5. This would be 0 to a. So we don't have to worry about the 0 because when we plug in 0, we just get 0. So we just have to worry about the a. So then we get a to the fifth over 3 minus 2a to the fifth over 4 plus a to the fifth over 5. So if I just this will equal to, this would just be 1/2. And this would just be negative a to the fifth over 6 plus a to the fifth over 5. And this would just equal to, I believe, negative 1 over 30. Oh, negative a to the fifth over, positive a to the fifth over 30. And then we got our integration. So we just solve for n. Should be 1 over 30 a to the fifth a to the fifth over 30 to the 1/2, and our normalization constant is equal to 30 over a to the fifth over radical. So does that make sense to everyone?
Yeah.
Yeah.
Okay. So that's it. So basically, if you're doing a problem like this, just worry about the boundary conditions and just integrate based on that. All right. Now we're up to uncertainty principle. So uncertainty is pretty, I think is pretty okay. If you're asked, they're probably going to give you a question like, oh, find the expectation value of this operator and then find the expectation value of this operator squared. And then you'll probably say uncertainty, calculate the uncertainty of this. And so basically all you would do is just take this radical on this radical other side, and then this will just equal to and uncertainty is just basically saying, okay, how good is this expectation value I'm measuring? So it's the expectation value of this operator. So if we were talking about x, we would find the expectation value for x squared, and subtract it by the expectation value of x, and then we square that, and then we go 1/2 power. All right. And these are just the uncertainties for different values for particle in a box. Let's put particle in a box here. And there's a Heisenberg uncertainty principle, which basically says you can't measure the uncertainty and momentum accurately at the same time. One will be really good measurement, the other one will be a all right measurement. And this is greater than or equal to. Okay. And we're going to go on to commentators next. So a commentator is basically just saying, can I measure with these two operators, can I apply both of these onto a wave function and measure both of these at the same time? And if it's 0, that means I can measure them equally and they have similar sets of eigenfunctions, which means they commute. And if it's not equal to 0, they don't have similar sets of eigenfunctions. I don't know why I put that here. Like a common set of eigenfunctions, I mean, and they do commute. And then if it doesn't commute, that means they don't have similar sets of eigenfunctions. And the momentum operator, based on the uncertainty principle, the momentum operator and the position operator don't commute, meaning I can't measure both of them with good precision. All right, so this is just an example to calculate the following commutators: momentum operator squared with the x operator squared. Okay, so the first step for calculating commutators is basically use an arbitrary function. Like f. So based on this, we would a commutator is basically just an operator, so you just do this. And after expanding it, we saw from our definition that this is what a commutator equation is. So we just do p, so p of x will be negative h bar squared, derivative operator squared. And it's just x squared times the function. And this is subtracted by x squared times negative h bar squared, the derivative operator squared. We'll have to do a momentum operator. I'd like to take out negative h bar out. And then from here, so the hardest part of commutators, if you're includes derivative, you have to do a product rule. If you're trying to do a commutator with like a variable like x squared or x. So we had to do a product rule 2 times because we have a second derivative. So you first do the product rule with whatever's on the side here. So it's going to be 2x, and that's going to be times the original with the function, and it's going to be plus, and then you're going to do derivative for this one. Oh wait, just put that here. And then that's going to be whatever it's inside here. And that's going to be x squared times the first derivative. And it's going to be minus x squared. And we pulled out negative h bar out. So that's going to be f double prime. Because we just have to take derivative of this. And that's pretty much the operation. And from here, you would see that negative h bar squared. And we do another product rule with two terms this time. So it would be 2 times f plus 2f double prime. And this will be plus plus 2x times f prime. And that's going to be, so make sure I'm doing this correctly, 2x f double. Oh, yeah, it's single prime. That took the first derivative. Okay, and then that's going to be, the next term is going to be plus x squared times f double prime. So from here, we can cross out some terms. We can cross out this, we can cross out this. And then this will just add together to make 4x f single prime. And what you're going to get is just negative h bar squared. And it's going to be 4x f prime plus 2f. Okay. And so a commutator is basically just an operator. So we have to separate the arbitrary function by the rest of the operations. So to do that, we see that we have h bar squared, whatever's on the inside. So we have 4x, and this is f prime. So we take out the derivative out of f prime, and we get 4x, the first derivative. And then we have just f. So we just can just put plus 2. Because 2 times the original function, and then that we have f. And this will be, it'll be negative h bar squared. And this will be your commutator. Let's call this commutator omega, and this will be your commutator here. Does that make sense to everyone?
Yeah, I think so. I think like once I go over this, you go over the second example, it'll make more sense.
Okay. I'll tell you about the second example. It's pretty much a trick question, and it's pretty easy to do based on your first one. But
I have a question.
what do you say?
Wait, so what is the answer? Just 4x plus 2?
It's negative h bar squared, parentheses 4x derivative plus 2.
Oh, it's the whole thing. Okay.
It's the whole thing but f, because a commutator is just an operator. So we don't want to include f in our answer because that's what we're operating on.
Okay, just drop off. Okay, thank you.
Okay. Before I move on, the second part's I'm not gonna really do this again in the second part. So does anyone have any questions on how I got this at all?
No, I think I'm okay.
You okay? Okay.
Yeah, I'm also good. Yeah.
All right. I'll just tell you, it's just basically applying product rule 2 times. I think that's the hardest part about this problem. Anyway, let's go to part B. So from our definition of commutators, we found that this is true. This is just but we also found that let's imagine if we were to switch these around, right? Then this is just going to be equal to BA minus AB. And if you guys really think about it, if you were to multiply this by -1, you get and now B minus BA. So if that's true, then this must be true. Now, based on this fact about commentators, can you guys guess what this answer is? It's because B is basically just the operators are switched around, right?
Yeah, it would just be
Is
like
it
the
just
positive
A
version. Yeah.
Yeah,
or
it'll be the
negative
original
A?
times, yeah, it'll be the original times, the
-1.
original, yeah, times -1. So it would just be h bar squared times 4x derivative operator plus 2. And just use this fact. If you're doing a commentator question and it asks you this question, it's like easy points. And if you guys are like unsure about if you got part A right or not, like let's say if it's a different question, you're unsure about it, then I would say do this in reverse to see if you get the answer but negative, just as a check. That's only if you're really unsure about it. And I would save this for the last if you're like, oh, if I'm unsure. Okay. So after that, we're gonna go with particle in a 3D box, which is pretty much almost towards the end. So energy is additive, meaning that you can add energy together, and so that means the Hermitian operators are additive. And to make sure that these are additive, we have to multiply the wave functions by different parts. So let's say if we have x, the operator for x in the x direction, y direction, and z direction, we have to multiply each of the wave functions for x, y, and z together. So that means that if the energy is additive for particle in the box, you can add each of these components together to get this equation below, where it's Lx or Lx, Ly, and Lz are both lengths of the box, and Nx, Ny, and Nz are both quantum systems for each of the dimensions. Does that make sense to everyone?
I think I'll get it when there's an example.
Okay. I'm just basically saying, since energy is additive, you can add each of the directions together. So basically the same thing. The equations are the same thing, and you could just add these together, and you can just simplify it, distribute this term out. All right. So degenerate just means if the number of different ways can lead to the sum of, and so it's basically this here is just reliant on the sum of whatever's inside. So if I were to add this, like if I were to have different quantum numbers, like let's say 111 or 112 or something like that, there can be different ways that you can arrange this to have different energies, and these different combinations can lead to same energy. So for example, like let's say we have to add up to have the inside equal to 3, right? We can there's only one way to do it, which would be if it was a cube 111, meaning that there's only one way to do it because you can't change any of the column numbers to where it's going to be equal to 3 in the inside. And for 6, there's going to be 3 different ways for 6. So the generosity is 6. And it's going to make much more sense by going to example problems. But yeah, this is it for this part. And this is just to tell you what the box looks like. So it's basically like a one-dimensional box, but just 3 dimensions this time. And for a cubic box, since L's the same, just simplify L out. So L is the same. This will be, you can simplify L out of this equation. Okay. All right, kind of saw this beginning, but I'll just guide what I did basically here. So consider a particle in a mass m having a length Lx and a length Ly with Lx equal to 2Ly and V of x equal to 0 inside the box, write an expression for the allowed energy levels of the system. So let's go to our original equation here. So since we only have 2 dimensions, we don't need n and z, and we don't need this term. So we only have whatever's here. And they said that Lx equal to 2Ly. So to make sure I don't have any fractions, I'm gonna make everything in terms of Lx. I mean, just 2, so divided by 2. Let's make everything in terms of Lx, so that way that the fractions, there's no fractions in it. And I'm gonna call this term W, so I don't have to write it again. So this is gonna be equal to whatever's inside W, and then this is gonna be equal to n x squared over Lx squared. And this is in terms of, so it's gonna be ny squared over, since this is Lx over 2, we just distribute, substitute. That's going to be it squared, and then this will equal to W nx squared over L squared plus 4 ny squared over Lx. And we can just simplify, and this will just be the original. Because I distribute out the Lx, this will just be nx squared plus 4 ny squared. Does that make sense to everyone?
Yeah.
That sounds unsure. You got confused at a certain part, or?
Yeah. Can you go back to how you put the very beginning?
Oh, so what I did in the very beginning, so I basically put everything into W, so I don't have to write it again. And the box is telling you that this is Lx is equal to this. And so what you can do is you can put everything in terms of Lx or Ly. I chose Lx because I don't want any fractions. Because when you have a fraction here, this is going to be at the bottom, and fractions when they're on the bottom do the reciprocal of it. So when we put this on the bottom, the 2 will go up and it'll be 2 squared, and it'll be 4. Does that make sense?
Yeah.
Yep. Okay, and right after that, I just distribute out the variable out at the end. So I just left with this term.
Okay.
All right. Now, the next part is to find a 0-point energy. And they're asking why is it 0-point energy? So basically the 0-point energy is always 1, 1, or in 3 dimensions, 1, 1, 1, or 1 dimension 1, because n can only be as low as 1. And so just plug in 1 for this, and then you're going to find it's going to equal to 5W. Does that make sense to everyone?
Yeah. Thank you.
Yeah, I get that.
Okay, it's going to ask us to calculate the first 8 energy levels. So I'm not going to do that. I'm just going to basically calculate the first 6 or first 4 if I'm like tired of this question. But all right. So
Did
we
we
have our
learn
first
this?
energy level. Yeah, I think you guys did, right? 3-dimensional.
Oh my god. I was not paying attention. Okay.
So in order to solve this, would you just like plug in and then find the 6 lowest answers?
Yes, you would just plug in to see which is the lowest ones. And I'll give you guys a kind of trick for it. This helps you with the first energy. I think the first 2 or 3. But
Okay.
so the lowest is always 1, 1, because that's as low as the quantum numbers can be. I might do 6 or 5. 1, 2, 3, 4, 5, 6. So it's going to be E of 1, 1, which is going to be equal to 5W. All right. So E of NX and Y. So I'm going to put everything into a variable called W, so I don't have to worry about writing the term. It equal to NX squared plus N4NY squared. And this is going to be squared, times W. So what you're going to do for the energy levels is you increase the thing that's not multiplied by a whole number integer by 1, because if I do, I'm going to get something that's next and lower. So in this case, nx squared would be not multiplied by anything. It's not multiplied by 4 like the other one here. So I would increase it by 1 for the next energy level. So I do E21. And that's always the next energy level. So that's going to be, okay, so 2 squares, that's going to be 4 plus 4 times 1 squared, which will equal to, that's W. And that's just 2 squared. Let's put it in, okay. And that's going to be equal to 8W, which is the next energy level. Now we can do E of 3, 1. And we can also increase it by E of 2, 2. So trying to test out these two to see which one is higher yet. And then we would,
sorry. Continue,
okay.
Sorry.
So, all right. So we do 3 squared plus 4 times 1 squared times W, and that's going to be equal to 9 plus 4, which is 13. Right? Yeah, 13W. And then we have 2 squared plus 4 times 2 squared W, and that's equal to 2, so that's 4, and that's going to be 16, that's going to be 20W. So this is the next one, and we're going to put this in the back of our mind when we calculate the next one. So this is going to be E of 3, 1, and that's going to be equal to 13W. The next one is E of, let's try 4, 1 this time. And this is going to be 4 squared plus 4 times 1 squared. And that's going to be 16 plus 4, which is 20W. And these are both degenerate energy levels. And it's asking to see any degenerates. And these are 2 degenerates because these energies are equal to each other. So there's 2 ways of getting this energy level. So this would be E of 2, 2, 20W, and this will be E of 3, 1. And these are both degenerate. Okay. And then from here, we can calculate, let's try E of, let's try E of 5, 1, E of 5, 1, then E of 3, 2, and And then the next one would be E of 4, 2.
Wait, I'm sorry to interrupt. Is the top one you put supposed to be 4-1, or is that just another 3-1 and I'm getting
Well, which top one?
the one you pointed out as degenerate? Maybe the one that's 20 W. Is that 4-1 and 2-2, or is it also
Oh,
3?
yeah, it is. Sorry.
Oh,
Thank
okay,
you.
okay.
Thank you.
No, sorry, I was just confused.
Okay. Thank you for pointing that out. Okay, so basically we calculate this and we get 5 squared plus 1 squared times W, and that's going to be equal to 26W. And then we have 3 squared plus 2 squared times W, and that's equal to 9 plus 4, which is, oh, I missed one.
Isn't it supposed to be 29?
This here?
Yeah, for 5-1, isn't it supposed to be 25 plus 4?
Oh yeah, 4 times 1. Yeah,
And then the bottom one, yeah.
yeah, I just figured it out. I was just thinking to myself, wait, that's a little too weird. Okay, so 5 squared. Okay, so that'll be 29W. And this would be 4, so it'll be 4 times 4, 16. That'll be 25W. Yeah, and then 4 squared plus 4 times 2 squared. I think this will be higher, so
32.
16. Yeah, 32. Thank you for pointing it out. And so let's go with, that'll be 25 next one, so it'll be 3, 2. And let me just check if these 6 ones are correct. Okay, and give me this. Okay, here we go. Let's see. All right, 1, 1, 2, 1, 3, 1, 2, 2, 4, 1, 3, 2. Okay, and these first 6 are correct. Does that make sense in how we got these?
Yeah, it does.
Okay, yeah, yeah. The trick is basically. Oh, what's
sorry,
up?
no, were you saying something? I don't want to cut you off.
Oh, that's no problem.
Okay, so I just got here, so I'm a little confused on the degeneracies in general. So do you just keep going number by number? Like,
Yeah, yeah.
how does that work in general? Sorry, if you just explain the
So
concept to me.
yeah, so degeneracy is basically, so we use this equation here, the equation we made, and it's in 2 dimensions. So it's going to be like a based on nx and ny. And for the first question, all we're doing is making an equation based on the equation for equation for 3D particle in a box. In this case, the 2D particle in the box, and they always give us parameters for like what nx and ly are in terms of, and from that you solve for this and you plug in what you substitute what ly is or lx is based on what terms you want to put it in, and then based on that you make an equation, and this equation will then tell you to make degeneracies. So like I plug in like 1, 1. 1, 1 is always the lowest one you're gonna have, and then you increase it by the lowest one that's not multiplied by an integer. So in this case, it would be nx because not multiplied by like 2 or 1 or 4. And then this will be the next one. And then from there, you're just trying out terms like, okay, I add it to the lowest one to see if this is good, or I add it to the other one. So in this case, I tried 3, 1 and 3, 2. I increase it by 1 here, or I increase it by 1 here. And if this is lower, I go to the next one, and then I see if this is going to be higher than the one I previously calculated. Does that make sense? And
So-
degeneracy just, oh, what did you
So
say?
I keep cutting you off. I'm so sorry. So do you just like cap it at 6 because the 6 energy levels, like so like the two numbers add together has to be 6?
Oh,
like-
you just cap it at how much they ask you for.
Oh.
In this question, they ask you for 8.
Oh, so you wait, I'm confused. So you just, but do the values matter? Like after it does, like it says calculate like the energy and the degeneracies. Does you just put out the values, or does it have to be like a certain value? So I don't get the part where you said like if it's bigger than.
Oh, when it's bigger, so basically what I was saying is you calculate the values. You're just pretty much just testing out values. And if it's we're trying to get to the next highest one. And so when we're trying them out, we're trying to see the next lowest one. So the lowest one we put as the next one. And then after that, we find another one that's bigger, and then we pick that as the next lowest one.
Oh, I see.
And
Thank you.
And degeneracy just means that the energies are both equal to each other.
I see. Thank you so much.
Yeah, no problem. Okay. So consider a particle mass m box. All right, I'm just gonna do the first part because I think you guys know how to calculate part B. It's pretty much just plug and chug. So, so part A is asking you write the formula for the normalized wave function for 3, 2, and for the particle in the state nx equals 3 and ny. So we know that for each direction, it's the wave functions are going to be kind of similar to each other. So for x is going to be equal to 2 over Lx, and that's going to be sine of pi n x over L of x. And then since it's asking us for 3, 2, this is going to be the third, the quantum number is going to be 3. So I'm just going to erase this into the rightness again. And then for in the y direction, the quantum number is going to be, so it's going to basically be the same wave function, but except with Ly, and it's going to be sine of pi, and the quantum number is 2 this time. Yep, it's 2x over Ly. Okay. And since they're both equal, the length of the box are both equal to each other, you can just put this as L. And what you would do to get the final wave function is multiply these by each other. And you would get this is equal to 2 times 2 over L, and this is sine 3 pi x over L times sine of 3 pi y over L. Yep, and then this will just equal to, so this is just 2 of it, and this is L squared. This is just going to be equal to 2 over L. Now, does that make sense, guys?
Yeah.
We can just leave it as that.
Yeah, you can just leave it as that.
Okay.
That's your final answer. When you think of normalized wave function, people always assume that you have to integrate, but you know the form of the function. And if they're asking you this, but they're asking you for psi of z2, you just make the function. It's just going to be exactly the same as this, but each variable is with a z, and whatever quantum number they specify, you just plug in that for it, and you just multiply it to this function too. So it'll be like this for if it's a 3D box. All right.
Wait.
So
Wait. Oh,
It could be
sorry.
two.
Alex.
Yeah, is it 2? Wait, where did the square root go?
Oh,
You're
because you're
multiplying
multiplying just
the
by each other.
Oh, yeah, true,
Yeah.
true. Okay. But would the second one be 2? The first one be 2? Or whatever one's y? Yeah, shouldn't it
Yeah.
be 2 pi y?
You have 2 3 pies. I thought one of them was supposed to be 2 pi.
No, it is 2 pi. Oh, yeah, I see what you mean. Yeah. Thank you for telling me that. So yeah, it's 2.
I was
You
gonna ask if
have
you
it.
can do 2b really quickly.
All right, sure.
Yeah, because I'm really lost.
Yeah, it's perfectly fine. So based on this equation here. So you have 2 directions, and Lx and Ly are both equal to each other. And so you just plug in. We simplify out, since Lx and Ly is equal to each other, this is just L squared and L squared. And so we can simplify L squared out. And then we have Nx and Ny, which are just both. So Nx is just 3 squared plus 2 squared. And then this is just going to be equal to pi squared h bar squared over 2m L squared. And that's like 9 plus 4, which is 13. Yep.
Oh, okay. I thought it was like a different formula. No.
Yep, it's it's just plugging, chugging in. That's pretty much all you have to do. Okay. Let's see. You guys learn about particle in a 1D box yet? Like tunneling at all?
I don't believe so. But also, I haven't been to lecture in a while, so.
We were going
Oh.
to particle, but I don't know if we did tunneling yet.
Okay.
You guys-
I think I heard. Oh, what about to say?
No.
I'll just quickly review it just in case, because I got a curveball at this last time, and I got a 0 because of not a 0 on the test, 0 on the question, but it's pretty. I think it's hard at first, but I wouldn't say it's hard. I would say it's like, as if you apply it, like think about it, it's like makes sense. So let's imagine there's a particle m moving in a 1D box. I mean, not a 1D box, just moving, right? And the wave function can be described it moving to the right as so this is to the right, the red. I should pretty much even pointer more. So it's just moving to the right. This can be described by this here. If it's moving to the left, it can be described by this wave function here. So, and this shows wave-like behavior, because if you were to do e to the I alpha, this is what it is. So the wave function will be kind of like waves. So from here, let's say that the particle is moving, and it goes over a barrier. At first, it's gonna have no potential energy, and it's gonna have, and then before it reaches the barrier, and after it reaches the barrier, it's gonna have potential energy. So, and this energy is higher than I forgot to specify that this energy, or kinetic energy in this case, is higher than the potential. So the potential barrier that you crossed before. And since the particle at first doesn't have potential energy, the particle is going to have an energy of, the particle is going to have an energy of just kinetic energy because it's only moving forward. And the energy here is just going to equal to, is E minus V of X. Okay, so its original energy subtracted by V of 0. Oh, okay, And so from solving the Schrodinger's equation, you're going to find that this equation describes the first one in this region describes what the particle's wave function in the first region. And so we have this term here, which describes the particle going to the left. So there's a probability of the particle going, and before crossing that barrier, it turns back. And then for and A describes it going to the right, as we've shown from here. Now, and K1 can be described with this equation. And this is just K1. And the second term describes the particle entering like going over the barrier, and since the particle is past it and won't be able to hit anything, you don't need the second term. The second term describes it going to the left, but it's always going forward after it crosses the barrier, and it goes over the barrier because the energy is higher than I'll just say the energy. The energy is higher than the potential barrier energy. Does that make sense to everyone?
Actually, yes.
I'm gonna be honest, I'm confused.
Okay. Let me repeat it again. So the particle, right? It has it's at first, it's just traveling in free space. Doesn't have any potential. Does that make sense so far?
Okay.
I'm saying right as its position, as it goes to x equals 0, it's about to pass over a barrier. And the wave function before it crosses over the barrier can be described with this wave function right here. And so it has a probability of going back. That's why we have this term here. Does that make sense? Because it's probability of going into the left, and we've shown here that the wave function to the left can be described with this equation here. This negative I kx. And this is it going straight, like going to the right. 100% with that, guys?
Yeah, okay, I see the left and right now. Okay.
All right. And then after it passes the barrier, the wave function can be described with this equation. And it's going to be always going to the right because it's not going over a barrier after that. It's just going straight through the barrier. Now, does that make sense?
But isn't it
Yeah.
negative? So
It's not negative because it's moving to the right.
But for the first region, I was able to move to the left.
Oh, because it's quantum mechanically, it can move to the right or the left. So that's why we have both terms. It's moving to the right, but there's a probability before it crosses the barrier that it can go, it can just like not pass it. And that's what this B here describes.
Okay, so there's no barrier to the left of to like -5 or something.
Yes,
Is that-
exactly.
Okay, got it.
Yeah, oh, I should just like, what I'm doing, I should just do this. This makes much more sense. Okay, do you guys have any more questions about this? All right, so I'll
No.
go on to the, oh, you have one?
No, I said no, I don't have any more.
Okay. So then we have the second thing here. So this time the particle is crossing the barrier, but the energy is lower than the barrier's energy. And because of that, it's gonna have so the wave function in region 1, so in this region, can be described by the same one in the first region before it crosses the barrier. Now the particle can bounce back with B. The only thing that's different is that since the energy is lower than the then the energy of the barrier, which is v of 0, this will have a wave function described by this, and it's not going to be negative I, it's just going to be negative k1x. And this makes sense because if I cross a barrier, if I'm just penetrating through the barrier, like, and it's the barrier has higher energy, then that means I'm gonna have a decay, meaning that as I go through that barrier, I'm gonna have a decay. There's like a less probability chance of me going at higher x's to see that particle there. Does that make sense, guys?
Can you repeat a higher what? That last part?
Okay, so when it reaches that higher x value, you're not going to see that particle, because it's basically saying I'm tunneling through this barrier, and there's a less likely chance at higher x values that I'm going to see that particle that particle.
Oh, okay.
So you're saying like it's like losing speed almost. Is that what you're saying?
It's kind of like saying I'm least likely to penetrate the barrier at higher x values. It's pretty much saying, okay, I'm trying to go through this I'm trying to dig through this like this wall, and I'm just like a tiny particle. There's like a little chance as I'm going higher and higher and higher at higher positions that I won't be able to see that particle.
Also, that's what the slanted red arrow represents, right?
Yeah, that's what I'm trying to like say right here. And it's not going to be it's not negative I, it's negative k of 1x. So, and I'll just erase that. Okay. So, and we reject this term, which is k of 2. Oh, this is k of 2. Which is k of 2x, because this means that this will be increasing, and that doesn't make any sense. It will just it will make the wave function the probability density infinity if you include this term. All right, are you guys all good with that part? You have any more questions that need to be answered? All right, if you do, I'll just read through your notes and stuff, because that's how I learned this topic after I lost points on this, but yeah. All right, so let's go on to boundary conditions. So we know that wave functions have to be continuous. So the wave function has to be connected at x equals 0, and this is x equals 0. And so because of that, it has to be continuous. The wave function has to be continuous. So both the wave functions at each region have to be equal to each other, and their first derivatives have to be equal to each other. And this is the solution after applying that. So I plug in 0 for the previous one, and I equal to each other. So I equal this to this when it's both equal to 0, and we're gonna have this. And then for this, I take the derivative of this equation, and then this equation and this equation, this equation and this equation, and then I plug in 0 for it, and this is the boundary conditions for it. And a squared is the probability of it turning right, and b squared is the probability of turning left. And the probability of reflection is described by this equation, the probability of transmission is described by this equation. Is everybody go with that part? I think this part is really not that important, but I think this part here, this describes how each term relates to it turning right or it turning left. And boundary conditions are important too. And I'll show an example later on. Everybody okay with that?
Yeah.
Yeah.
Okay,
Actually, hold up.
all right.
For B, you said that that's how it goes. Like there's a probability of bouncing back, right?
Yeah,
Like, what if it was traveling to the left instead of to the right?
yeah,
What we always see.
if you're saying if the particle were to start out here,
Mm-hmm.
if it were to start out here, then this region will be described by this wave function here. Because even though it's basically in the barrier, it could still bounce back here.
Wait, can you show me again with like the laser pointer?
Yeah, sure. So if this was here, it'll be described by this wave function
Uh-huh.
because it's going to be exiting out the barrier, which means that it could possibly bounce back again. But after that, it's just going to go straight, like straight, and without it turning back because there's no way for it to stop and bounce back.
Okay.
All right, and that goes to our example here. So this is the question that, oh, let me just get something real quick. There was a picture for this question. I just want to grab it. There we go. Okay. Okay. Consider a particle mass m moving in a one-dimensional under a piecewise potential. In the region that corresponds to x over x is less than 0, the potential v of x is equal to v of 0, which is greater than 0. Okay, it describes this region here. And in region 2 that corresponds to x is greater than 0, the potential is equal to v and x is equal to 0. If the particle is shot from x equals negative infinity in the positive direction, E is with the energies is greater than v of 0 and v of 0 is greater than 0. See the figure in the next page. Okay. Which of the following region corresponds to the wave function 1 in region 1? Okay, so this time you're going to ask to do this in the reverse direction. And so a particle is shot from this direction here. All right, so from here, guys, what wave function would you guys think would describe the particle here?
See?
Well, I thought it was A1 or A2.
Why would you think it's A1 or A2?
Because didn't you say
Oh,
like
wait,
we
oh, wait,
needed like
oh, sorry, you continue.
because you were talking about that it needed the left and right aspect or something like that, and that A meant right and then B meant left.
Yes,
So
that's exact.
Okay.
Oh, you can okay. You want to say something else
No,
too?
that's
Or
all I have. No, that's all I had.
okay. Before I just and let's give me 1 second, guys. Give me something. Summary. Okay, so it's between A1 and A2, so it would be A1. Because if you had both these terms here, these would diverge as you this would diverge as you go to negative infinity. So you would have to have the I terms here. So in this case, it will be A1. This will be A1 for the first part. All right, and it's asking which of the following corresponds to the wave function 2 in region 2. And I forgot to include the other part, which is on me. There we go. Okay. So what do you guys think would be the best answer for this? Let's put this down. So I'll remind you that the particle is moving in region 2, it's moving in this direction. Now, what do you guys think would be the best answer for this? B1, B2, B3, or B4?
I was thinking it's between B3 and B4 because it doesn't have a restriction, so it doesn't have to go left and right. Is that
Which between B3 and B4 you said?
right? Because like it's only going one direction, it doesn't go left and right, like in part
Yeah.
A.
Yes,
Okay.
you're correct. Yeah, so in this case, I believe it would be, it's always gonna go to the right. And so you're gonna have this term here, which means it's going to the right. And this would be, it'll be B3. And let me just double check if the answers are correct. Yep, okay, yep.
I have a quick question.
What's up?
Is it the coefficient that determines whether or not it goes left or right, or the exponent?
It's the exponent.
Okay, so negative exponent means left and positive exponent means to the right.
Yes, and if it has that I term, you have to the I term has to be included in that too.
Okay, thank you.
No problem. And just note if it's crossing the barrier, then it's gonna be a no I term. So if it's going to this direction, let me get the pointer out. In this direction here, and it's crossing below, like in the barrier, then there will be no I term. It will be described by this. Okay. Now it's gonna ask which of the following conditions corresponds to, oh, I already answered that. What are the boundary conditions that impose on the wave function? So all you have to do for this is basically plug in or take the derivative. So has to equal to this. 1, 2. So basically you just plug in 0 for this and you just get A plus B equals C, and that's your first boundary condition. Take the derivative of the wave function for the first region, and you'll have IK1 times A e to the IK1x and that's going to be plus negative IK1, and that's going to be B e negative IK1x. And then for 2, you would just have C e IK1, IK2, I mean, x times C e IK2. All right, and then from here, you would just plug in 0 for it and equal to the other side. So that'll be, and let me simplify this out. So it's going to be A minus B, and you'll equal to the other side, which is and that's going to be equal to IK2, oh, IK2 C. Yeah, IK2C. And that's your answer. And let me just double check again. Yeah, exactly. That's the answer. So all you have to do with boundary conditions is use the wave function, just plug in 0 the first time, and then take a derivative and then plug in 0 the second time, and equal the wave functions to each other for both regions. Does anyone have any questions about that? All right, does anyone have any general questions? Because that's the last of my review.
Okay, can we go back to the generalities part? Because I think I was still a little confused on why we went from. Wait, could you go back to that slide?
Yeah, sure. All right, what's your question about?
So why did you go from 3-1 to 2-2? Like, what made you go from those two numbers?
So I increase, so based on this equation, my best course of action is to increase the thing that's not multiplied by something to get the lowest energy level. When I'm plugging in, I just plug in, so like I first start off with the first energy level, which is 1, 1, which is always the lowest one. And I increase this one because if I increase this by 1, you're gonna always have the next energy level, and so you're gonna have 8W, which is just all the constants together. And how I got from 3-1, I test out two values. So let's say if I were to increase this one by 1, this would be 2, 2, and I got 20W. And then the next, let's say if I increase this by 1, I get 3, 1, and I get 13W. So I'm pretty much just increasing each one to see which quantum level gives me the next lowest energy level, and that's how I'm like going to the next one. I'm testing out different values for nx and ny to see which one is higher. Does that make sense?
Honestly, no. I think it's a simple concept, but for some reason it's not getting through to me. So from what I'm getting is that you want the lowest value, or like or do you want it to be bigger than the one you got before?
Oh, I'm starting from the bottom and I'm
Right.
going up. So I want the next highest. So when I want the next highest, I want to make sure that there's no energy level before that that's lower.
Oh, wait. So why did you go from like? So why didn't you just do 4-1 after 3-1?
4-1. Oh, because I test the value before, and turns out this one's lower than 4-1. I mean, it's not lower than 4-1, it's the exact same one as 4-1. So these ones are
I
both
see.
equal to each other. They're both
So-
degenerate. That's why they have equal energies.
So you wanted to like label them in order basically, and 2-2
Yeah.
just happens to be. Oh, I see. So you want, okay, so just like the lowest combination in order. So why'd you?
Oh,
Go
Wait,
on. Sorry.
wait.
You got it.
I was gonna say why you didn't do 1, 2. Like
1,
1,
2?
comma 2. Yeah, because I think that would be 17.
Oh,
Isn't
yeah.
the lowest 1, 1 though? Or can you do 1, 2?
Yeah, you could do 1, 2. I just realized that.
Yeah, I was like looking, I was like, something's missing. But yeah, go on. I was just curious.
Okay, so let's say if I try 1, 2.
Did you do 1, 3 also?
1, 3?
Yeah.
I think I did too.
I think 1, 3 would be too big. 1, 3 would be.
1, 3 would be too big. But you could do
1,
that,
3 would,
right?
yeah, it would be like 37. Wait. Yeah.
Okay.
Times W.
So in reality, when we're on the test, we're actually trying out like a bunch more than this, right? Like on our
Yeah,
work.
but they're probably going to ask you like 4, and you can definitely get the first 2.
Oh yeah, I see.
Yeah.
This makes more sense.
Yeah, so this would be between here. That's what's a killer with this type of problem, is just first getting to try different ones, which killed me. So
Also, would 3D box just be a more complicated version of this?
oh yeah, it definitely will. But I doubt he'll ask you something like that.
Okay,
Maybe
thank
he'll,
God.
yeah. So if he asks you about something like, if he does ask you something like that, he'll probably ask for the first three and its degeneracies. But I high possibility he might say it's a cube, then it will be easy from there. Because all you would have to do is just increase it by one. So you have like E11, E21, and E11, E21, and E31. But if he asks you for like include the first three energy levels and include degeneracy, then it's just gonna be E11 and E21 and then E112. Because if he asks you to increase degeneracy and it's a box, then you can switch out the two with an utter end value. Does that make sense?
Wait, how come you were using two values for a 3D box? I mean, for a box.
Oh, this is a two-dimensional box.
Oh, I thought you were talking about 3D. I'm sorry. Okay.
Oh yeah, I mean, I was using a box. I mean, when I was saying like 3D box, yeah, I was saying E11. Oh yeah, E112. Yeah, I see what you mean. Yeah, so, I just forgot to mention that. But anyone have any other questions?
I do. Can we go over recitation to number 7? I don't know if you have that. You probably do though.
Station 2, number 7. Let's see. Recitation. What's number 7? What did number 7 say?
Oh, you guys didn't have it last year. Okay. I will share my screen. Give me a second.
Okay.
You guys see it?
Yep.
Okay. So it says a particle, you're given the mass. It's a one-dimensional infinite potential well. And this is the width, wavelength, and then the activities.
Let's see. I think I remember this. Okay, so particle, okay. What is the quantum number for the state of the particle? So I think it's saying, remember the next energy level equation? So you're supposed to use that, and then you're supposed to, from that, you calculate the wavelength, which is,
I think in this problem they use something called the
Broglie.
Bogado principle. Oh yeah, Broglie principle. And they set the energy equation like pi squared h bar squared over 2m equal to something. they canceled a lot of variables that then ended up with like a equation. Something I forgot.
HC over.
Oh. I don't know if it's recording my screen. So can someone else hit like record real quick?
Oh, it's recording.
Oh, okay. Awesome.
Yes, that's a record. Yeah.
I'll try it again. So this time I'll do HC. And I'll just do minus. And why is it doing this to me? It's minus, and then let's subtract it. Okay, I think you're supposed to do this, get the energy equation, and then subtract, and then plug in n plus 1. I mean, yeah, n plus 1. That's what. That's why, yeah, n plus 1, and plug in n and en, and then subtract the equations by each other, and then solve for n, if that makes sense. Because I think he teaches you this 50-50. If he does, you when a particle or anything increases energy level, it emits a photon, and that photon is related to this equation. I think it's h, yeah, Planck's constant times c over the wavelength, which is given.
When it increases state or decreases?
It can be either or.
Because doesn't it emit a photon when it goes from a higher energy level to a lower one?
I think it's lower. Oh, wait. Whose mass is 1 part k. Yeah, a lower to a higher to a lower. You're right. Or a higher to a lower, because it's the same energy forwards and backwards. So you can use this equation too.
Could you explain K?
Okay.
Like K equals 2 pi over lambda. Like how is K derived? If you know.
Equals 2 pi
Over lambda.
is so 2 pi over the wavelength, right?
Yeah.
Wait, Kevin, how'd you get that?
I'm not sure.
It's week 3, the Friday's lecture. It's like 5th to last slide. It's the Broglie relationship thing.
So it's not really a derivation. I think it's something that they wrote just to save on space. So they probably had this term like 2 pi over lambda a bunch of times, and then they just used k for it. Oh, I don't know what k. I think k describes just the basically just 2 pi over lambda. I don't know how I can like explain it more. I just say it's just a constant that they use just to save on space. I'm writing a term.
I think K is used in like P equals K bar H bar. Px equals KH bar. And they used it to like solve the equation that Shinji is talking about.
Oh, they use it in this here. Okay. Wait.
Well, let me see if I can take a picture or something.
See if particle is fast. Okay. Okay. That's here. Let's see. This is um,
Do you guys see the solutions for this question? Because I can't. I don't think I see it.
The solution.
Yeah, for this one, recitation 2, number 7.
It's a. Oh, he did. It's in lecture. Week 3 Friday.
okay, so this is how you do it. K equals 2m over k. And that.
Why would they give us something in recitation 2 and they explain it week 3? I don't get that.
He gave this question like week 1, but then he uses a different method to solve it in like week 3, which is.
Okay, I'm gonna send you the solution by Gmail. So give me 1 sec.
Guys,
I
you
don't think
do
you
need
need
to
to-
know tunneling.
I don't think you need to know this for the exam. I never had to calculate anything like this. Oh, he does. Yeah, I remember this. He does solve this in a problem like this in during lecture. But the problem is so long that it wouldn't be in the exam. But
He gave us 5 minutes to solve this in lecture. I just can't.
Isn't that wonderful? For our quizzes, our weekly quizzes, he says 10 minutes. They really only give us 8.
yeah,
I've been taking L's on those. Oh my god.
I didn't get to go last week.
I sent you the solution. And I don't really know how to solve this. I don't remember going over this in I mean, I do remember going over this in lecture, but I never used something like this in recitation.
Great. I love being
But
challenged.
anyway, what'd you say?
I said I love being challenged. I don't.
Yeah. Okay, so I'm gonna go to sleep, try to find something to eat, and just send me the recording after you guys are done studying. I don't know if you guys are done studying or not, but
I'm done too.
Thank
I've
you
been
so
had
much.
enough.
Thank you. I've had enough.
Dimitri.
yeah, it's
Thank
no
you so
problem.
much.
I wish I can be a little